So welcome back, everybody, to episode 43 of the Quantum Science Seminar, which today will all be about atom interferometry. As usual, we would like to have your questions, so please send us your questions to quantumscienceseminar@gmail.com, or please use the YouTube live chat at the right or at the bottom of your screen. Also, please note that there's a 30-second time delay between what you see as live on YouTube and between what we do. And with that, I would like to hand over to Ofer Fürstenberg, who will introduce our speaker today.
Thanks, Sebastian. So it is a great pleasure to introduce today's speaker, Professor Philippe Bouyer, Research Director in CNRS and in Institut d'Optique in France. Professor Bouyer received his PhD at École Normale Supérieure in 1995. He worked back then with Jean Dalibard and Claude Cohen-Tanucci and Christophe Salon. From there, he continued to a short postdoc at Stanford with Mark Kasevich, where he studied ultra-cold atoms and, of course, atom interferometers. For both gravity measurements and inertial sensing. Following that, Professor Bouyer joined the CNRS and the Graduate School of the Institut d'Optique. He studied atom lasers and Anderson localization with Alain Aspect. And his interests span from quantum simulators with atoms to developing atom interferometers in various directions, from fundamental studies to applied usages. And so in parallel to all this, he also co-founded a company, Equivalence, which builds and sells gravity meters based on atom interferometers. Professor Bouyer is the recipient of the 2012 Louis Day Award of the French Academy. He's an APS fellow and an OSA senior member. So without further ado, it's a pleasure to host Professor Bouyer today, who will talk about quantum sensors with matter wave, from lab to the field. So Philippe, thank you for coming. The stage is yours.
Yeah, well, thank you very much for the introduction, and thank you very much for the invitation, even though it's virtual. So I will try to, on one hand, give you an overview of what we are doing with quantum sensors, and also make you travel a little bit from underground to the air, basically with the experiments we've been performing with those quantum sensors. But straight to the point, when I will speak about quantum sensors, I will basically speak of two major quantum effects that we use in order to do precise measurement. The first one is quantum superposition. Let me see if... hold on a second, I'm sorry. It doesn't want to. Okay, I will just stop sharing and start again, because it seems that it doesn't want me to change my... No, okay. Sorry for that. It should work again. Okay, sorry. So just, yes, so the first fact is the idea of quantum superposition, and it's basically the basic idea of atom interferometry is that any quantum system can actually evolve in a superposition of multiple paths. And when you want to look at the probability for the system to evolve for an inertial state to a final state, you will have to sum the amplitudes of all the paths and then compute the probability. And by this way, basically, you can have some effects of interference that will enhance or hinder the probability to evolve or the probability to actually be in the final state. So that's the first idea behind quantum sensing and matter wave interferometry. The second idea is the fact that matter wave is a direct consequence of basically the duality between a particle and a wave. So a wave is usually described by a frequency and the wavelength. It's the typical periodicity of the oscillation of this wave. And the particle will be described, of course, by energy and momentum. That's the two complementary parameters for that. The concept of duality was introduced by Einstein at the beginning of the last century to explain the existence of the photon. And it was then extended by Louis de Broglie, who was a French chemist, who generalized this concept of matter waves to any kind of particle, including atoms or electrons, by introducing the de Broglie wavelength, which is written here, and which is basically the analog of the photonic wavelengths, except that the de Broglie wavelengths will depend on the inverse of the mass of the particle and the inverse of its velocity, or in other words, the inverse of the momentum of the particle. So this de Broglie wavelengths, we will use them associated with atoms, and we will basically use quantum superposition to engineer some path on which these particles can evolve, two different paths in this example, which is a Mach-Zehnder interferometer. And at the vertex of this, these trajectories, we manipulate the particle by using atomic mirrors or atomic beam splitters. And as I will show later, we were basically in what I will present in this talk, use light in order to manipulate these wave packets. So we use this quantum superposition, this coherent superposition, to create this coherent splitting and build this interferometer. And at the output of this interferometer, as I said before, depending on the phase difference between the two paths, you will have a modulation of the probability of the particle or the atoms to exit in the output port, the upper output port or the lower output port. Here on this graph, you have actual data. Each point represents one experiment where we look at the probability of the atoms to be either in the top or in the bottom output port of the interferometer. And as you see, because you have a phase difference, then you have a sinusoidal modulation of the probability. So the key element in order to build this atom interferometer is this coherent manipulation that will split the matter wave in two different parts that can fly apart from each other, or that can basically redirect the trajectory so that they cross again. What we have been using for our type of interferometer is our lasers, or in other words, standing waves, in order to do this manipulation. And the basic idea behind this manipulation simply comes from a two-level atoms. If you take two states, a ground state and an excited state, that are separated by an energy, then if you shine a light which is very close to this energy, you will induce a transfer from the ground state to the excited state, or from the excited state to the ground state. And actually what happens if you shine the light is you will have a Rabi oscillation, an oscillation between the ground state and the excited state at a fixed frequency, which only depends on the parameter of the atoms and the intensity of the light you're using. So that comes basically from energy conservation. The energy you transfer from the light is used for the electron to go from the ground state to the excited state. But of course, you have also momentum conservation, which means that if the atom absorbs a photon, it also absorbs its momentum, which explains why the excited state will have a different velocity from the ground state. And this is how you create basically the beam splitter. An atom going through this laser will actually be split, both in a state which is a ground state and an excited state, but also in two states that have different momentum. And this is how we can actually build our interferometer. Here you have an example of this Rabi oscillation between the state which is diffracted and the state which is not diffracted. So that's the three key elements for making an atom interferometer. We have to engineer some source of matter wave, which in our case will be done by cooling atoms, using laser cooling or more advanced system to get ultra cold atoms. Then we just select the atoms that we can use for our atom interferometer, and we send these atoms into a series of light pulses or a series of light gratings that will split, redirect, and recombine the matter waves in order to create these two paths of the atom interferometer. And because they are in two different states, we can easily detect each output port of the interferometer by simply looking at the different states by using, for example, fluorescence spectroscopy. And then we just record the interference fringes. So that's the basic idea behind building an atom interferometer. Now, I told you that this modulation comes from the phase difference between the two paths here. So how can we understand what will affect basically this interferometer and what will affect this phase difference? Again, you can use the principle of quantum mechanics by simply looking at the integral of anything that will affect the classical trajectories that are drawn for this interferometer, so the upper path or the lower path. The way to do that is just, for instance, to compute the Lagrangian and to integrate the phase over those two trajectories. When you do that with your atom interferometer using light pulses, you find out that you will have two different components, two different origins for the phase difference. The first one will be basically everything that can affect the trajectory of the particle, the classical trajectory of the particle over the space. And that's basically what can be affected by inertial effects, because your atoms have a mass, or any kind of phase fluctuations that can come from interaction between the mass and a field around it. Another effect actually has to be taken into account in this case is the fact that at each time the matter wave crosses the laser and interacts with it, as I said before, you exchange energy. This is how your atom goes from the ground state to the excited state. You exchange momentum. This is how we built this interferometer. But you also exchange information about the position of the center of mass of your matter wave into the light. In other words, the phase of the light at the position of the matter wave will actually be imprinted to the matter wave itself. And this phase is actually read out as a phase difference at the output of the interferometer. So there are these two different parameters. And if you do the complete calculation, you find out that because, if, for example, if you want to look at inertial effects, because acceleration or rotation will change the trajectory, the classical trajectory of the particles, then the phase only comes out from this second term, which is the laser interaction with the matter wave. So that gives you a fairly simple picture of how you can actually use a matter wave interferometer for inertial sensing. This simple picture comes from the fact that you take your atoms, your matter wave that you created by cooling atoms at a very low temperature, and then you let them evolve, for example, under the acceleration of gravity. In this case, your atom will fall down, which means that the trajectories of your interferometer will be bended towards the bottom because of this acceleration of gravity. And then you just compute the phase at each crossing between the trajectories and the laser which is used to create this quantum superposition. And what you find out is it as if you were basically measuring extremely precisely the distance the atom travels from the first pulse here to the last pulse there. Or if I just compress this picture, it's like I have the 3 points, which are the three position of the atoms at each time I have an interaction. And then this distance here is measured very precisely by comparing it with the phase reference, which in this case is just the distance between the two lobes of your standing wave. And it's as if you were measuring basically this distance with a very precise ruler. And of course, if you compute that, even if you compute it exactly, you find that the first order of this calculation gives you exactly this term, which is here. The distance is g times t squared, half times g times t squared. And your laser reference is just 1 over lambda in this case. So you compare the two distances, and this is how you get your phase. This simple picture really helps to understand why these sensors can be very interesting and what are also the things you have to take care of when you want to use this type of sensors. First, why are they so interesting? If you just compute the expected sensitivity of such a sensor, let's suppose, for instance, that you have a signal-to-noise ratio of 1000, which means that you can detect phase difference of 1 milliradian, or in other words, that you have about 1 million atoms contributing to your signal, and that you have a time distance or a time difference between your pulses, which is 1 second. So your interferometers last for 2 seconds of measurement. In this case, the minimum acceleration you can detect will be of the order of 10 to the minus 10 meters per second squared. And this is 3 to 4 orders of magnitude lower than the variation of gravity, which is, for instance, induced by the tides. So this is just to tell you how small and how precise this sensor can be. If you want to translate that, for instance, into just a change of the height of your measurement of gravity, this corresponds to less than a centimeter, like a millimeter or something. So it's these very tiny changes that you can measure. But it's not only that, because the phase term only depends of time and wavelengths. It means that the scale factor of your measurement, how you translate the acceleration you want to measure into the quantity that your sensor is giving to the instrument, the scale factor is very well known. t is very well defined, and the wavelength is also very well defined. So your sensor will be very exact and very stable as well. And the only thing that can actually be affecting the measurement is the fact that your ruler is shaking. It's like if you want to measure something, if you're shaking, you won't measuring very well, which means that you will have to be very cautious about the stability of the phase of your laser when you do the measurement. And I'll come back into some examples I've been doing. So just to summarize, when you when you engineer a quantum sensor using matter wave, you have a sensor which can be extremely sensitive, which can be exact. So sensitive means that you can detect tiny changes of the quantity you want to measure. Exact means that when you measure something, you know that the result of your sensor is exactly the quantity you're measuring, and not so stable, which of course means that if you measure it one day and then you wait bazillions of years before measuring it again, and the quantity you want to measure did not drift, then you won't see any drift. Or if you see a drift, then you know it doesn't come from your instrument, but it's really a measurement of the quantity that changed. So just to translate that into some applications, the stability is usually what, or the accuracy is usually what you're happy with when you build a clock, stability and accuracy, because it defines the time so well that, for example, 1 second is defined with a precision over 100,000 or hundreds of millions of years. But if now you translate that into a gravity measurement, the sensitivity is so big that you can actually detect water underground, like tons of water, like large masses of water buried kilometers deep, or small masses of water buried 10 or 100 meters deep, without having to drill. And if you're thinking of acceleration measurement, because it's not drifting, then you can be sure that you can navigate with an accelerometer without GPS, so with no need to recalibrate your measurement over days. And I will give you some of the example of applications that we have been studying in our laboratory in the recent years. But just to finish with this brief introduction, these sensors are today not only available in the lab, and I will show you some experiments that come from the labs, but they are now commercially available. So lots of work has been done in the last 20 years in order to make this sensor useful, compact, and now you can buy a commercial quantum gravimeter, which is exactly based on this concept of manipulating the atom with light. And the fact is, this system is now usable by someone who doesn't hold a PhD in quantum science. So you just need to plug in and press the start button or the turn on key there, and then you record the variation of gravity as you see on this graph. This is just the variation of the tides I was mentioning before, induced by the difference of the position of the moon, the Earth, and the sun, that changes the tide of the ocean, but also the shape of the crust of the Earth. So that's about having a commercial system, but a transportable one, because they can be operated on boats. But I will mostly focus on 3 applications we've been studying and we've been developing in our laboratory that will make us travel from underground, where we are starting to build a large atom interferometer to detect gravitational waves, to space or to microgravity, where we envision to test general relativity with this type of systems. So let me start with an underground sensor network in this case. I will explain a little bit more about this concept of network. And this is basically a French project, which is called an équipement d'excellence. So it's a large equipment that we want to build in Rustrel, which is in the southeast of France. There is an underground laboratory there. So I don't know if you see my mouse. I can't see it anymore, but so it's on the right in the picture. You see just above Italy. You have some mountains there where in the last 60 years it was the site for the nuclear tactical force of France, and it's been decommissioned, and now we can use this underground laboratory for experiments. And here we will build a network of sensors that on one hand will be used to detect gravity gradients fluctuation in order to perform some geodesy study, and which is also be a premise of maybe the future development of gravitational wave sensors. So how can we expect to detect gravitational waves with matter wave interferometry. So let's just remind you what the detection of gravitational waves is performed nowadays. So as you all know now, there are lots of events that have been detected, like collisions of neutron stars or collisions of black holes that have a signature with gravitational waves. And the way to detect that is to detect the compression of space-time by just looking at the change of the time of propagation of the light between two proof masses. And this is done by laser interferometry in LIGO in the US or Virgo in Europe, in Italy. And the proof masses in this case are mirrors that are suspended so that they are isolated from any vibrational noise and they behave like proof free mass at a certain frequency. And you just record then by interferences the length between the distance between the two mirrors. And this distance is compared again with the phase of the light. So this is how you look at it. So sometimes we say that we are monitoring some distance modulation because of gravitational waves, but what's more accurate to say is you basically detect a modulation of space-time, which is modifying the time the light takes to go from one mirror to the other. And this time is actually read out as a phase difference in your interferometer. This works extremely well. The signals we want to detect are very tiny, even if they are very big objects that create these gravitational waves, black holes, for instance. But because they are so far away, what we have on Earth is only a tiny modulation of this space-time, of this length, which is equivalent to femtometers or even less than that, 10 to the minus 18 of a kilometer, typically. And in order to detect that, you need to be isolated from any other noise, in particular, for this type of sensor, the vibrations that come from the coupling of the mirror to the ground. And because of that, the sensitivity of these sensors is limited to a frequency above a few hertz. But there are much more to see if you go below these frequencies. This is why, for instance, you have some projects for space where you can go to very, very low frequency. And this is why we are also looking at the opportunity to use atoms in order to look in a frequency band which is between these optical ground-based detectors and the future optical space detectors. So why do we think that atoms can actually help at that level? First, because you can have atoms as free-falling masses without having to hold them against gravity with a wire like you would do with mirrors. So in this case, they can be isolated from any other vibrations coming from the ground. But there is another effect that you need to take into account when you are working on ground. It's the fact that your instrument will be actually close to a large distribution of masses. And when I say large distribution of mass, it's, of course, it can be the soil, it can be rocks or mountains, but it's also the atmospheric variation, the clouds coming there. So because you're trying to look at such tiny effects, any small variation of density can be actually read out as a gravitational wave passing by at the frequency you're looking at. And this is actually a major problem for gravitational wave detector, which is called in the community gravity gradient noise or a Newtonian noise. And this usually limits your ability to detect gravitational waves below a few hertz. So what we hope to do with atoms is not only measure the distance between 2 points or the time of flight of the light or the phase difference between 2 points, because this is actually what we're measuring, the phase difference, but to repeat this measurement at many different positions using the same laser, but different atom or different matter wave that will actually go through this laser at different places. And with that, not only can we measure whether there is a change of the distance that comes from a gravitational wave, but we can also measure some tiny spatial signature, like changes of distance that will not be linear. And this will basically come from mass fluctuations, closer mass fluctuations. And this, we showed that can actually really help to remove this gravity gradient noise or this background noise, which, by the way, is noise for gravitational wave detection, but it's actual signal for geophysicists from the actual measurement. So this is also why this instrument is not only potentially a very good gravitational wave detector, but at the same time, the signal can also be used in geophysics just to study the mass movement around the instrument itself. So how do we want to perform that? We need to reach a very low sensitivity. As I said before, typically the strain you want to measure, which is the differential length variation, is of the order of 10 to the minus 17 or less than that. So that's super tiny. So in order to enhance the measurement of our atom interferometer, we want to put a cavity and the laser in the cavity, as it is done for Virgo, for instance. The cavity enhances the power of the light, and it enhances also the interaction between the light and the atoms, and thus will allow us to actually reach this type of sensitivity. And this is what we are currently building for this instrument. There are many advantages for cavities. As I said, more power. Actually, also the cavity filters the laser mode, so it cleans basically the light so that it's almost perfect for interrogating the atoms, and it cleans the light both spatially as mode filtering and also in frequency, so that the laser wavelength is actually extremely well defined. But there is a challenge with cavity. There are actually two challenges. If you want to try this experiment on a small version of your instrument, then a small cavity means that the size of your modes, so the waist of the laser, will be very small, thus reducing the interaction area between the atoms and the light. And if you go to very large cavity, then the weights can be large, so you can have a very good interaction, but then it will limit your ability to make short pulses in order to interrogate the atoms. So we try to study and solve those two problems. How can we actually have a large cavity in which we have such a control of the interaction between atoms and light so that we can make very short pulse, which means that the atoms will only interact with the light at very short times? And second, can we make a smaller version of this experiment with a large waist? So to answer the second problem, we found that basically what you can do with atoms, something that you cannot do with other systems, is to control independently how the atom can interact with the light. And this is an example here of what you can do with an alkali earth atom, this strontium in this case, in which the interaction to create the interferometer has to be done between the ground state and the excited state, as I said before. But of course, an atom is much more complex than that. You have many, many states, and then you can use the coupling between the states that you're interested in with other states, using, for example, lasers in this case, in order to modify the interaction energy between these two states so that they can be out of resonance with the interrogation laser or in resonance with the interrogation laser. So if you turn on the light, it's in resonance, for example, and then you turn off and it's off resonance. So it's like the atoms is completely transparent to the light and nothing happens. And in this case, you do not depend on whether you're able to turn on or off the light in the cavity, but only whether you're able to turn on off or off the light when your atom is crossing the laser. And in this case, we showed that you can actually independently create pulses to make this interrogation without being limiting by the lifetime of your light itself. So that's the first aspect that we are studying in order to solve one of the problems of the cavity. The second one is, of course, before building a very large interferometer, is to be able to perform some experiments in the lab. And in order to do this part, we've basically designed another type of cavity, which is basically a semi-degenerate cavity. So semi-degenerate means that your cavity is barely stable. Usually, if you want to have an optical resonator, you will engineer your cavity with some curved mirror so that even if you have a small change of length or a small change of alignment, then you still have the light traveling back and forth into the cavity, and you still have this enhancement of the power. But of course, this leads to a very small mode volume. What you see on the top left of the transparency here is now if we use flat mirrors, which is usually the worst way of making a resonator, a stable resonator, but you include an element into your cavity, like a lens in this case, you are able to still get a stable resonator, so enhance the power of your light. But in this case, the waist can be much larger. And in this way, we can actually test atom interferometry for larger geometry, but we can also perform atom interferometry in such a small cavity just to study it. And these are on the right 2 examples of atomic fringes, Matter wave fringes that have been observed with this type of system. What you see here is a modulation that changes with time, which means that we have a slightly tilted experiment, so it's measuring gravity. And when you change time, you change basically the dephasing induced by gravity, because it depends on g times t squared, as I said before. And what you see here is exactly this, a modulation where basically the phase changes as g times t squared. We've done that also with another configuration when there is not only 1 photon exchange, but 2 photons or 3 or 4 photons exchange, so that the interferometer is much more sensitive. And it's the top, the bottom right of this transparency. What you see is that the fringes are oscillate much faster on the green than on the blue, which means that basically you have a phase sensitivity, which is much larger, coming to this enhanced sensitivity of your interferometer. On the bottom left, you see a top picture of the small version of the MIGA instrument. Small means that here the scale is only 10 meters. The distance between the 2 interferometers will be about a couple of meters. Now, of course, this is just a preliminary experiment. We are currently building the big one. The big one is built 400 meters underground. You see here a few pictures. The little a, the photo little a, labeled little a, is the underground galleries where the system will be installed, and the B and C are some tubes, vacuum tubes and vacuum chamber that we will assemble in order to build this very large underground interferometer for gravitational wave detection. And I think I will make a break for questions right now.
Okay, thank you very much, Philippe, for the already very clear talk and introduction you are giving to atomic interferometry. So we do have many questions. So we have many of them from Bill Phillips. So let's start with that. So Bill would like to know, could you say more about the idea that the phase in the interferometer is determined only by the phase written on the atoms by the laser beams that act as beam splitters or mirrors? Because he says this cannot be generally true since something happened between the laser beams applied to one arm and not to the other, which will certainly affect the interferometric phase.
So yes, Bill is right. This very simple picture that I gave is valid when you want to measure inertial effects. So this is only for some fields that have a certain dependency and that acts on the 2 arms at the same time, in some sense. So basically, the formula I gave for acceleration is valid, and it can be only calculated by the modification of the trajectory coming from the inertial effect. But if you have something happening on one arm, like if you put some gas, for example, or something that can affect the phase of the matter wave on one arm and not the other, of course, this will not be true. So in general, you have to compute the phase difference of the interferometer using these 2 terms. It's only valid for inertial effects.
So another question that he has is, could you compare the performance of a quantum gravimeter and a classic one with a drop corner cube? How do they compare?
So how do they compare? So basically, if I take back the commercial gravimeter that I presented from Nuquants, nowadays the performance are typically at the same level, which means that, so we speak about microgal. A microgal is 10 to the minus 9 G. So 1 part per, 10 to the minus 9 G, 1 part per billion of G, and this is about the same level for the falling corner cube. The accuracy is a little bit better than that. It's a little bit below this level for the falling corner cube. It's about the same level as well, maybe a factor of 2 less for the cold atom interferometer. Basically, the best sensitivity is obtained with another type of gravimeter, which is called the cryogenic gravimeter. It's basically a sphere which is suspended by a force, but it's using cryogeny, which means that it's not exact in the sense that when you install it, you need to calibrate it with, for example, a falling cord or cube gravimeter.
And then a third question he has is the use of an atom interferometer as a detector or proof for mass of a gravity wave interferometer compatible with the use of squeeze light in the interferometer?
That's a very good question. So I'm not sure. Well, okay, squeeze light is, well, I try to answer it the way I understand the question. So today, squeeze light is used in gravitational wave detector in the sense that it's very hard to increase the power of the light in the laser, in the optical resonator, simply because then you have too much power on the mirrors, and the thermal effect will actually degrade the sensitivity. So in this case, squeezing helps to get signal to noise ratio without having to increase the power. So now the squeeze light so far does not really change the way the atom interferometer will actually see the phase difference. There is no obvious effect of squeeze light into the way we manipulate the atoms. On the other hand, what we are studying, or people is studying, is to squeeze the matter wave itself. So have a squeezed number of atoms in the interferometer in order to improve the signal to noise ratio.
Mm-hmm. So this, I think, also answered another question that we had in the chat from Saison Kim, which was if you use squeeze light for your measurement light or for your beam splitter light, do you expect to see the enhancement? I guess this is also.
Yeah, this is about the same answer, I think.
And we have again another question from Saison Kim in the chat, which is, are you limited by the noise of the light, such as noise of the beam splitter light or measurement shot noise of light or so?
Not limited. So what will limit us eventually at the end, and that really depends on the configuration of measurement you're using, for example, 2 arms versus 1 arm and etc., is not the intensity noise of the light, but mostly the frequency noise of the light. Of course, they're related, but it's mostly the phase noise. So the frequency noise will actually translate to phase noise, and the phase noise will actually translate to phase noise in your atom interferometer. So that's what we have to be careful of.
Mm-hmm. And now when we think of your cavity scheme, the atoms are illuminated by the light in the cavity, which is always on. Yes. Through all this interferometric trajectory. And if I understand, then your scheme would be to light shift and put this light on resonance or not in the specific points where you want the beam splitters.
Yes.
So isn't this going to introduce extra possible sources of noise or like instabilities in your system? Did you evaluate that? How does it?
Yes, so we did some evaluation on that. Of course, the atoms are passing through the cavity itself, so they don't spend so much time in the cavity itself because they are launched upwards and then they go across the beam and then they eventually go again. So they spend a little more time in the light field than they would spend actually being manipulated with this light field itself. So there is a tiny effect. So this is why you need to have a trade-off between the disturbance of your light, which is used for manipulation, the light you will use also for this, so turning on and off the interrogation. And there is a short range of parameter that you can use in order to actually get the proper accuracy. We evaluated that.
Mm-hmm. And maybe just a very last question. We have many more, but just for the sake of time. So what are the perspectives of building massive particle interferometers based on objects larger than individual atoms?
So there are some ongoing experiments. There are some very nice experiments using more complex molecules than atoms in Vienna, in the group of Mark and Arndt in particular. And there are also some prospects to use heavier particles like microspheres or nanoparticles to make this type of interferometers. Of course, what's nice with our atoms is first we know them very well and we control them very well so that we control all the parameters on all the disturbance. having heavier particles has some advantages for some type of studies, like, for example, if you want to study a gravitational coupling or gravitational decoherence, it might not be so obvious that it will help a lot for gravitational wave detection. The mass does not really enter into account there.
So I think for the sake of time, we need to go on, and we will take more questions at the end. So thanks.
Okay, thank you. So let me go on with another experiment where we think atoms can actually play a significant role in testing another aspect or another consequence of general relativity. Here it's more an aspect than a consequence. It's one of the cornerstone of general relativity. It's actually a cornerstone of general mechanics, which you can state as the question: what falls faster, a feather or a hammer? And that actually, it looks like an obvious question. Usually you ask this question to your kids just for fun, but it's actually a fundamental one. And as an example, Aristotle believed that they would not fall at the same speed. And it's only since Galileo who introduced the famous experiments, formerly supposedly on the Pisa Tower, that introduced this equivalence principle that basically every object falls at the same time in the same gravitational field, no matter its nature. So this is called the equivalence principle, and this is something we want to test with atoms. So usually, up to now, these tests have been done with much better precision than the hammer and the feather, but still using classical particles, even classical artifacts. One of the best experiments nowadays is done in space with two artifacts rotating around the Earth, and because the satellite is in free fall, these objects in the satellite, isolated from any disturbance, are also in free fall, and by just looking whether they are displaced with each other after many rotations, you can actually test the equivalence principle, and it's tested at a very good level, almost 10 to the minus 15, to my knowledge. So what we want to use in this experiment are atoms. And atoms are interesting because first, you can really place two atoms at almost the same place at the size of the atom, which is very tiny, so that you really check the gravitational field at a scale where they are almost identical, or they're really identical. So this is much better than artifacts. And another advantage with atoms is not only can you change the nature of the atoms, two different atoms, which is what we studied in this case, but you can also change eventually the spin of the atom, the internal structure of the atom, so you can change isotopes, which means that you have many more degrees of freedom that you would have with artifacts. So that's some ideas that really motivated many groups to start experiments on testing the equivalence principle. So our group in Bordeaux, but also in Hanover, Stanford University, and Wuhan, and in Florence. But the basic idea is always the same: is let's not build only one atom interferometer or Malloy wave interferometer, but two that we operate simultaneously at the same place. So we take two different atomic species, as shown here, and then we just drop the atoms and measure the acceleration brought by each of the interferometer simultaneously. So of course, we want to use, in our case, potassium and rubidium, because the mass is very different, a factor 2, but the wavelength is very similar, which means that the scale factors here, as I said before, in this case, it's 2 pi over lambda times t squared, is almost similar, still, we need to adapt that in order to get the two atom interferometer almost overlap for the measurement. So we've performed this experiment, and I will just give you some brief results on that, because there's still a lot of work to do. So so we did two types of tests. One on the ground, which is not the best one. Some of the best ones have been achieved on large drop towers at Stanford University. This one is on a small experiment. Now I'll explain you why. And another one that was performed in a specific environment, in microgravity, basically, just as a premises of what you can do in space, where you expect to really push the sensitivity to its limits. So we basically, the test on the ground was done with exactly the same device that is used for the microgravity test, and this is why it's actually not designed on the ground to be very good. So what you can see on the graph anyway is that you can build two interferometers that are not eventually super good in terms of accuracy and precision, but because they are common mode radar, then lots of noise is rejected, which means that you can integrate over long periods and have actually significant improvement in the sensitivity of the equivalence principle, which is this parameter eta, which is the Eötvös parameter, is simply the difference of acceleration radar divided by the absolute acceleration that the system encounters during the measurement. So how did we perform the experiment in microgravity? Well, in Bordeaux, we are lucky enough that we have a special plane, which is called the microgravity plane, or the GRG bus, in which first you can actually put an atomic physics lab. And this is what you see on this picture here. It's an actual atomic physics lab that is actually moved to the plane and operating while the plane is flying. And secondly, the plane is not flying exactly as you would expect from a plane, which means that it's flying in parabolic trajectories, so that when you're on the top of the parabola, the plane is actually similarly in free fall. It's exactly the same trajectory if you were launching the plane as a ball and then looking at the plane falling down. Of course, at some point, the pilot takes back the command of the plane in order to recover, and we can perform about 30 parabolas while we are doing the experiment. What's important there, and that was actually also interesting in terms of technology development, is that the plane is just the worst place to build a precision measurement. There are lots of vibrations, as you can see on this graph, and there are also lots of rotation, as you can see on the picture itself. And these two parameters affect the performance drastically of your sensor. First, acceleration. The fact that you have this noise of acceleration actually induces lots of fluctuations, like your ruler is shaking, as I said before. And because your ruler is shaking, basically you don't know what you're measuring. So when you read out the phase output of your interferometer, what you see is a random distribution of points, as you can see here. And you could think that you will not be able to measure anything with that system. As a matter of fact, if you look at the statistics of this, you find that the statistics is exactly the same as what you would expect if you are measuring precisely your sinusoidal distribution with a certain contrast and a certain signal to noise. And you know the scale factor because you know it by definition. So the only thing you need to know basically is where you're sitting on the fringe, because the acceleration is so large. So you do that by making a correlation between the classical acceleration of your mirror and the measurement of your accelerometer. And this way, we are basically able to reconstruct the acceleration of the plane by combining a classical accelerometer and a quantum accelerometer, and we then gain the sensitivity of the quantum system. And this, as I will introduce later, has actually some big, nice applications for navigation. The second aspect is more drastic, is the fact that when you're rotating, because your laser, which is inducing the velocity transfer of your matter wave, is rotating as well, it's inducing a Coriolis acceleration, which actually makes the two trajectories of your accelerometer fly apart from one another. And they fly apart in the perpendicular direction of the beams, which means that even if you look at this graph, you have the impression that the trajectory cross again. They do not cross. And then, in order to get some interference fringes, you need the spacing between these two trajectories to be smaller than the coherent length of your matter wave. And basically, if you now doing the experiment in microgravity for different types of temperatures, here in the case of rubidium, where we have a few microkelvin, and potassium, where it's about 10 microkelvin, you see that the contrast drops, and that's basically a measurement of the coherent length of your matter wave in this case. So if you make the coherent length longer, then you are able to observe a contrast for a much longer interrogation time or a much larger separation between the paths. And in order to do that, you need to cool down atoms to a much lower temperature. And this is what we have basically done, not flying in the plane anymore, but by engineering cold atoms in microgravity in the laboratory. And for that, we designed a big elevator, as you can see here. So this is a system that actually launches the experiments upwards by about 2 meters. And then this experiment is guided by some air bearing so that it is almost in free fall, and it actually reproduces exactly the trajectory of free fall. And in that experiment, we put some atoms, and we put some advanced laser cooling for atoms by using some gray molasses cooling. I don't have the time to give you more details, but basically engineering some dark states to cool down the sample at much lower temperature. Then we use this cold sample of atoms and we loaded it into a dipole trap, and then we used some evaporative cooling into this dipole trap in order to reach degeneracy, which means to make a Bose-Einstein condensate. I'm not entering into the detail of this here, but what's nice is because we have the control on the experiment, but also on the trajectory of the atom, we are basically able to start the loading and the pre-cooling of the cloud before actually we enter into the microgravity states, which means that we reach degeneracy and we reach the temperature for our Bose-Einstein condensate to appear when we start the microgravity phase, which means that then we have a full half second of microgravity to study quantum gases in this environment. So these are some examples of what we achieved in this, about 10,000 atoms on average at a temperature below 100 nanokelvin. And you find out that they are very, very cold, because if you look at them for about half a second, then you see that your atoms always stay into the interrogation volume of your detection. And so this is what we are currently working on, and we are just preliminary doing some tests of microgravity, of atom interferometry in microgravity. As you can see here, this is an example of a Bose-Einstein condensate, which is interrogated with some light, as I introduced before. And then you can take a picture of basically the matter wave split into different parts. Here, it's split in more than 2 parts, simply because we are using another type, another geometry on atom interferometry. And you see here some fringes that were obtained in this system. So, as I said before, this topic, on one hand, relates to testing general relativity and pushing the sensor to their limit of sensitivity. And on the other hand, it raised also the question of using this sensor into an environment which is basically an actual environment, a moving environment. And this was actually very interesting in order to start investigating some application of this quantum sensor, as I mentioned before, because these sensors are very stable and very accurate. You can actually hope to get them to give you information about your position without having to rely on GPS. So usually, if you want to navigate, the best way to navigate is basically to look where you're going. So this is what the basic principle of radio navigation, in which you're using beacons that you have on site, and then you triangulate your position by getting the distance between different type of beacons. And GPS work exactly the same way, by measuring the time delay or the time some information goes from your GPS receptor to the GPS satellites. Of course, this does not work if you don't have any satellites or if you don't have any direct view to the beacons. In that case, in order to navigate, you rely on information about your movement, or in other words, information about your acceleration and your orientation. And this is done by having some internal systems giving you this information, and this is called inertial navigation. Actually, we have some inertial navigation system in our body, but there are more advanced systems, and usually this is what is used for any type of navigation system, accelerometers and gyros, that you need to integrate twice. Of course, because you have to do this integration twice, then any small bias can lead to a very large position error, and this is why basically, usually, all this inertial navigation device need to be recalibrated from time to time with an external view, in other words, a GPS. So our idea was to start from the basic knowledge that we gained from that experiment I mentioned before in the plane. We can actually use the coupling or use the hybrid information coming from a mechanical accelerometer on one hand, and then a quantum accelerometer on the other hand. And if we merge these two information, where we can eventually get the best of both, which means the accuracy and the stability of your matter wave sensor, but also the high throughput and the high flexibility of your mechanical accelerometer. So how can we properly do that? That's something we try to address in order to see whether you can actually use this hybrid approach in order to build the future ultra-stable and ultra-accurate navigation system. So for that, we basically engineered a compact 3-axis matter wave interferometer, as you can see here, and we coupled it to a 3-axis inertial navigation system, which has in its box here 3 accelerometers and 3 gyros. And now we did the same approach, coupling the two, getting information from the classical accelerometers, but instead of using this in order to know where you are on the fringe to get information from the quantum sensor, we use the quantum sensor to basically recalibrate the classical accelerometer the same way you would do with a GPS. So it acts like an internal GPS without external view in this case. We use the classical techniques for that, like Kalman filtering, which is used for navigation, and showed that indeed, if you look on this graph, then the low frequency drift, which is here seen by this black curve, this is just like the accuracy degrading from your classical navigation system, can be basically compensated, and that's the blue and red curves, by using your atom interferometer. So the next step is to do that in a more practical way, on a more real way. So we actually put our system in this rotating platform here that actually reproduces the movement of a boat or of a plane. And using that, we basically devised a system that can measure the 3 axes of the acceleration at the same time. So we're really measuring the acceleration vector. And these are, again, some preliminary result of what you can actually achieve with that. So the 3 curves that go up at the end are each axis. And what you see here is you can get some misleading information about the orientation or the acceleration because of the drift of each of the axis measurement. But when you actually compute the actual vector, so this is basically in this case the magnitude of the acceleration vector, you can actually compensate and integrate it for a much longer time. So this is very interesting. In this preliminary experiment, basically each axis is an independent interferometer. So we measure one axis, then the other, then the other. And we are now looking at some more advanced matter wave engineering or quantum manipulation in order to build a 3-axis quantum superposition by using not only 2 beams, but 6 beams at once. And in this case, we hope to be able to build basically a matrix of atom interferometer, all in phase with each other, all correlated with each other, and that will give us some access to all the information you need for navigation. So that was the end of basically what I wanted to show today about what we are doing. Let me just finish by presenting the group in Bordeaux, in which most of the experiment have been done with many students and many collaborators, and hopefully when COVID is finished, I invite you to come and visit this very nice place where both we have some nice quantum sensors, nice wine also in Bordeaux, and we recently also have a quantum innovation hub that will be able to host many of you if you're willing to work with us or collaborate with us. Thank you very much for your attention.
So thank you very much, Philippe, for a beautiful talk. So actually we have a lot of questions, way more that we can answer in the time that we have left, I think. But I'm sure you will be willing to write some written answer to them otherwise. Yeah,
I'll do my best.
So let's start with some of them. So first, a question in the YouTube chat. So is there any way to use the spin property of atoms in an atom interferometer?
Well, that depends what you call the spin property. Basically, if you're speaking about different type of internal states, this is basically what we use today in some type of manipulation, because each path of the atom or each momentum state is also correlated to an internal state. Now, if you're speaking about, for example, spin gyros, which is really using the spin. This is another type of quantum sensor for gyros, which is used where you use the magnetic orientation of atoms, for instance, in order to get some kind of gyroscopic orientation. So far, what we have done with our type of interferometer achieved better sensitivity, but that's another type of matter wave sensor, or let's see, matter sensor, which is not completely based on matter wave manipulation.
So we have another question from Bill Phillips by email, which is precision atom interferometry with BECs has somehow been disappointing because of the atom-atom interactions in the high-density BEC. So is this a problem for you?
Yes. So, well, there are two ways to see it. So the fact is, if you have a BEC, there are lots of interactions, but then if you let the BEC expand, all this interaction converts into kinetic energy. But still, even after that, your BEC expands much less than a classical cloud of atoms, so that you can still have some enhancement of the sensitivity and the accuracy of the sensor. So you have to be very cautious indeed by expanding, let's say, your beam before you're actually using it for interferometry. I would make an analogy with light. I mean, if you have some nonlinear effects because of light, then you can reduce the intensity, or you can increase. So, and reducing the intensity means that you can increase the size of your beam. So we do the same with BEC.
Mm-hmm. And then a related question. So what is your view on trapped atom interferometry versus free space one, like the one you were discussing today? Well,
there are two ways to answer to it. The first is what we are most experienced with so far is free space atom interferometry, as I would call this one. Here we know that the atoms are mostly a perfect inertial reference, and then we interrogate that from time to time with a laser, and this way we have a very good control on all the fluctuations that the system can actually encounter for the measurements. So this is why we are still working with that to achieve the performance. Of course, there are limits to this type of sensors. The fact that your atoms are basically free falling means that they will move, means that they will also occupy like a certain amount of space, and so this will be a limit for miniaturization. In this case, it might be very interesting to go to trapped systems. There are many systems that we are candidates for that. I mean, maybe the best application is for rotation measurement, where you can really build something which is the equivalent of a fiber gyro, where the atoms are guided on a magnetic guide. But then, of course, you need to be very cautious about what can affect the sensitivity, which is all the interaction between the atoms and the environment, which is used for guiding.
So maybe just two last questions. So these sensors use the superposition of a single atom. So what is the challenge for building sensors that use the superposition of more atoms, something like GAZ states or something like that?
So that's the challenge is to get this these states at a certain level. So, well, there are again, I think there are many ways to answer that question. So the first maybe answer I could give is it interesting to do some squeezing for improving that? So to use some non-classical states in which you have a highly correlated states that can actually get a better signal-to-noise ratio below the shot noise limit. Of course, this is very interesting, but then you have to answer the question whether you are limited by the number of atoms you put in your interferometer, and whether the price of getting a factor 2 in squeezing is cheaper than the price of getting a factor 4 in the number of atoms in your system. It's a little bit the answer I gave for matter wave, for gravitational wave detection. Then there are very interesting prospects nowadays to use, for example, multiple particle interferometer, because you can create now, for example, bell pairs from atoms. So they will eventually be very interesting to study some type of effects, maybe not mature enough so far for practical application like navigation.
And just a very last question we have time to take. So what is the main motivation of testing the equivalence principle with higher precision? So are there any theories that predict this equivalence principle not to hold? So what new physics could we learn from that?
Again, I think there are, well, there are at least, I will give two answers to this question. So the first one is, or maybe many answers. And the first one is, someone told me once that we should never be satisfied by something that we cannot fully understand, or that we can always push further. So if at some point we find that there is a breakdown, that means that basically all the theory that we are holding to has to be revisited. It doesn't mean that it's not correct, but it means that to a certain level, it can be revisited. And there are some prospect of basically some violation of the equivalence principle coming from quantum gravity, coming from string theory, that needs to be tested. This type of experiment it's usually based on excluding some models in order to verify that we are actually still holding the good theory. So that's one motivation for pushing it. The other motivation, which appeared recently and which makes actually atom interferometry very interesting to that respect, is the fact that these atoms can couple to different type of fields, gravitational fields, dark matter field, dark energy fields, and they can then have some, for example, temporal signature that will be slightly different or unexpected. So if you reach that level, then you test the equivalence principle, but basically if you find some time dependence on that, you can again exclude or confirm some models that will give you some explanation about dark energy or dark matter.
Okay, so thank you very much, Philippe, for this beautiful talk and also for answering all these questions. There are still some extra that we hope will be answered in written form. So with this, I hand back to Sebastian for the final announcement.
Thank you very much.
Thank you also from my side, Philippe, for a very cool talk. I would like to take this opportunity to announce the speakers for our next hot topic session on April 22nd. We had a very large number of submissions this time, and we had a really tough time choosing 3. But we are happy to say that Maja Kalauiti, Daniel Gonçalves Romeo, and Tom Dara accepted our invitations to speak on April 22nd. But because we had so many applications, we're thinking of doing yet another session in July. So please stay tuned for that. Next week on April 17th, we will have Didi Leibfried from NIST Diamond Frequency talking about ion trap quantum information processing. And you should certainly check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Andrew Hauk speaking about superconducting circuits. If you want to get notified about what we do, you should certainly go to our website, quantumscienceseminar.com. You should subscribe to our email list and our Google Calendar, and you can follow us on Twitter also. With that, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.